So yeah, well, good afternoon, sir. So my name is Muhammad Giri, and for this occasion, I would like to present my assignment about orthographic projection. So let's get started. So orthographic projections, by the definitions, orthographic projection means that a projections of a single view of an object, such as view of the front, right, top, rear, or some of the view, into a drawing surface in which the lines of projections are perpendicular to a drawing surface. Or maybe simply we can say that orthographic projections are a two-dimensional representations of a three-dimensional object. So how can these definitions can be understandable? So let's jump into the example. For instance, we have this viewer, and we also have a projection plane here. And then the viewer would like to see some shapes like this, and what the viewer see over here will stay the same of the projection plane here. So orthographic projections we can say that this is a straight view of the object. So let's say this point is A and B, and also this point we will project this point into the A prime and B prime. So what the viewer see over here will be the same at the projection plane here. So that's why orthographic projections we can call it is a straight view on the object, because what the viewer see will be the same in here in the projection plane. Alright, next I would like to explain also about another example of the orthographic projection. So we take an object and draw usually three views of the object, like top, right, or maybe side view, and each view are created by looking at the object straight on in the direction indicated. So what does it mean? Like it means that if you see in the top view, it will be only like this in the surface. So there will be a circle here and the square here, like the top view. So the viewer is over here, and you will like see over here, this is the square one and this is the circle one. Then how about in the front view? So in the front view, like over here, I mean over here, so it looks like a rectangle one, and the top one is more like look like this, since this is a circle, but in a front view it is only like a square. And then last one is the side view. It is the same as the front view, but I guess this side one is more narrow for the length of the rectangle. So wait. And the next is I would like to present another example of the orthographic projections. So for instance, this is an object. So we know that this one is the top view like this, and then this is the front view, and this is the right side. So in two-dimensional orthographic projections, we will see like this in the top. If we project it, the top view will be this one, and the top will be here, and then the letter U like this, it will be here, and the same goes with the front. So the front, the letter L like this, will be here, and then this one, these shapes, it will be right here, and then the last one, this square, will be like this. So if we want to see the front view, it will be more like this, and the same goes with the right side, bottom side, rear, and the other ends. So since this only a three view, I would like to also explain about the sixth view of the orthographic projections. Even though we usually only draw three views of an object, there are six principles of view. Each principles of view are created by looking at each of six sides of the object. So this start from the left side over here, and the top side, and then rear side, right side, bottom side, and the front side. So yeah, this is the example of this object. If we look in the left side, so if we look in the left side, it will be like here, over here. So in the left side, most likely the object will be like this in the two-dimensional orthographic projections. And then in the front side, it will be the same like before, and then the top also the same, and then also the right side over here, and we will like see this one and also this one. And then the rear side, which means the back, it will be more like this. This one will be here, and then the letter L will be like here in the rear, and then the last one is in the bottom. So what most likely in the bottom is like this. So it will be a letter, what is it, letter E, or I don't know, but most likely it's like this, the bottom side. So it is here, here, and here. So this is the example of the orthographic projections in the specific object. So let's jump into the characteristic. In the characteristic, the orthographic projections, it needs a multiple view. What does it mean? It needs multiple view. It means that if you only took like a front view, or maybe only just top view, or maybe just left view, we couldn't know what the object is. So it needs a multiple view to complete to see the object. So means that if you look at the left side only, we don't know what is the shape is about. And then if only we see the rear side, we don't know also what the object it is. And then if we at least see the 3 or maybe 4 of the view, at least we know that what kind of object is that. So this both 4 of this view is part of this object. I guess that is explained before. And then the next one is it is have exact distance and angles. What does it mean? It means that if we take this one a shape, a square shape, and also if we have a projection plane here, and then what is the line of this line will be the same as this one. So same as like this. If we look at the top one, so for example this shapes, so the length of these lines will be the same as this one. So it have an exact distance and also angles. So yeah. And then the next one, it helps to build or construct specific object. It is for example, it is help for the architect who want to build some a good building, or maybe some a decent building, like this. So if the clients wants to need help from the architect, so the architect will draw some of the orthographic projections. So this is the example. It is from the rear side, and this is the side of the elevations, and this is the front, and also in the side left, or maybe in the side right. Which is most likely is like this for the characteristic. So yeah, and the next is I'm gonna explain about the matrix transformations, about the orthographic projections. So the formula of the projection transformations, especially in this 3D viewing, we have the VT equal PR1 times PR2. VT means the viewing transformations. PR1 means that it is a 3D viewing transformations, and then the PR2 means that 3D to 2D projection transformations. So the value of the PR2 will be the same. So let's get started of the example like this. So for instance, we have this this rectangle. So this we have A point, B point, C, and D. And then if we take a look like this point A and B, so A have an x1 and y1, and B have also x2 and y2. But but the both of the point will have the same z, because of they have one line in here in z. And then we're gonna proceed to C and D. It will be most likely the same. We will C and D. Oops, sorry, this is like this most D. So C and D will have the same point of Z. So that's why C and D have the Z2, and A and B have the Z1. So if we project this line A and C into the x and y axis, this line will be for the A prime. It will be x1 and y1, and the C prime will be x1 and y1. And since they are in the x and y axis, it will be z will be more 0. So it is same also in this one, B and D. So B prime and D prime will be more the same. It is x2, y2, and the D prime is also x2 and y2. And then what's the point if we already get this one? So the next is, we can also determine the x prime of the object. So x prime will be the same as x, and then y prime will be the same, equal y, and also z prime is equal 0, since the z is equal 0 here. And then how can we get that x prime is equal x? It is some like this. So the x means in the a prime and the a it's still the same, and also in the y prime is also the same. So by these equations, we know that the x prime means that 1x plus 0y plus 0z plus 0, y prime is 0x plus 1y plus 0z plus 0, and then z prime is 0x plus 0y and plus 0 plus 0z. And then if we convert it to the matrix, it will be most like this. So 0 1 0 0 from x prime 1 0 0 into 1 0 0, and then y prime 0 1 0 into 0 1 0, and then 0 0 0 will be 0 0 0. Sorry. Alright. And then if we take a look like this in the formula, so we know that PR2 will be the same as the it will be like matrix like this, and here it is the viewing transformations. So the VT will be like here, and the PR2 value will remain the same. And then so that how can we get the value of PR1? Since this matrix is the same as this matrix, so it means that we have an identity matrix. So that's why the PR1 result is identity matrix. So 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So this is front orthographic projections. And the next is I'm going to explain also about the right orthographic projections. So for instance, we have this cube in a two-dimensional object, and then assume that we have a viewer here who see in the front of the cube. But if we want to see the side view, the right side view of the cube, it is necessary if the viewer moves to here, or it is necessary we just rotate the object. So in orthographic projections, we don't need to move the viewer into the right side. We just rotate the object. So the viewer remains the same. The viewer will stay at the same spot, but the object, we just can rotate the object. So the object will be rotated like this. So the right side will be seen the front side. But how we can explain the matrix? Then, for instance, we have this kind of axis, y is to the top, x to the right, and z to the viewer. And then since that we rotate the object, the right side, this one is moved to over here, and then the x of over here will be moved to the z over here, and then z over here will be moved to the left. So that's why if we draw this axis again, so the right one is the new axis of this cube, since that we have it to the right orthographic projections. So z will be to the left, x will be in the x, and y still the same, since that we rotate in the y axis. And then so by that we know that the x prime will be z, and then y prime will be the same as y, and then the z prime will be minus x, since that z prime in here, and this is the opposite directions of the x, so that's why it is minus x. So by these equations, we know that the x prime is like this: 0x plus 0y plus 1z plus 0, y prime is 0x plus 1y plus 0z plus 0, and also like this. And then if we convert it to the matrix, the result is most likely like this: 0 0 1 for the x prime, and then y prime is 0 1 0 0 1 0, and then z prime is this minus 1 0 0, and then the rest will remain the same, 0 0 0 1. So we know that this matrix is the right orthographic projections. It's this PR1 of the right orthographic projections. But if we convert it to the viewing transformations, so we go back to this formula again: Vt equal PR1 times PR2. It means that Vt equal PR1, this matrix, times PR2. PR2, the value is still remain the same. So if we calculate this both matrix, the result will be like this. So 0, 0, 0, 0, 0, 0, 0, since all of this is 0. And then next is about left orthographic projections. So assume that we also have this cube again, and then the viewer is start with the front. And how about if you want the viewer who want to see in the left side? Sorry, like this. So before it is from the right side, and now it's on the left side. The process is remain the same. So we just only need to rotate the object. We don't need to move the viewer into the left, but we only can just rotate the object into the left. So in the left will be like will be see in the front object. So if we draw in the axis, it will be more like this. It is consists of x, z, and y. If we already rotate the object, it will be more like this. So the left one, so this one will be right here. So the z is moved to the z right here, and then the x over here is mostly like that over there, and the y is still remain the same. So it is the example of the left orthographic projections for the axis itself. So yeah, after we know this axis, we can conclude that we have the x prime is equal minus z, is y prime is equal y, and the z prime is equal x. Since that z is in x and x prime is in minus z. So by these equations, we know that x prime is like this: 0x plus 0 minus 1, and also y prime is 0x plus 1 plus 0, and then z prime is also remain the same. And then after that, we know that we have this matrix, and this matrix are representative of left orthographic projections. So if we calculate this formula again into Vt equal PR1 times PR2, so the PR1 is this matrix, and the PR2 is still remain the same. And then after we calculate this both matrix, the result is most likely like this. So it is the result of the matrix transformations for the left orthographic projections. And then how about the rear one? So it is remain the same. Assume that we have this cube again, and then if we want to see the viewer, it is front, and this viewer also who want to see in the rear. We just need to rotate the object, and we don't need to move the viewer. So for instance, like this, we have this kind of axis x, y, and z, and then if we already rotate the rear one, so it will be more so for the rear one, it will rotate like this. So the x, it will be minus x, since that we rotate to right and right again, or maybe left to the left. So it will be twice rotate in the left side, or maybe twice in the right side. So that's why the x, it will be most likely is minus x, and then y still remain the same, and the z prime is minus z. So after we know this kind of axis, we can conclude that x prime is minus x plus 0 plus 0z plus 0, y prime is 0x plus 1y plus 0z plus 0, z prime, and most like this. And then after we get this x prime, y prime, and z prime, we know that the matrix is most like this: minus 1, 0, 0, minus 1, 0, 0, and then the y prime is 0, 1, 0, 0, 1, 0, and the z prime is 0, 0, minus 1, 0, 0, minus 1. And then after we know that this is the rear orthographic projections, then if we go back to this formula again, the viewing transformations is equal PR1 times PR2, and then we get this matrix. So this matrix from over here, and this matrix is remain the same as the PR2. And then if we calculate both this matrix, and then we got this result: minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. And then next is the top orthographic projections. It's if we have this cube again, we assume that we have this cube again, and then the viewer is the front view, and also the viewer is also want to see in the top view. So the viewer who want to see the top view, so again we just need to rotate the object. We don't need to move the viewer to the top. But how about the matrix transformation about this? So assume that we have this kind of axis, and then after we rotate, then the y will be in the z, and the z axis, it will be the minus y. So the y over here will be moved to the z, since that we are moving top to the front, and then the z over here will be moved to the bottom, since that we move from top view into the front view. So and the x is still remain the same, since that we rotate the object in x-axis. So after that, we know that x still remain the same. X prime equal x prime, y prime equal z, and z prime equal minus y. Z prime equal minus y. So that we know that we have these equations, x prime, y prime, and z prime, and then we also know that this is the matrix for this one. After that, we get the top orthographic projections. Then we move again to the formula of the viewing transformations, equal PR1 times PR2, and then PR1 means this one times this PR2, and then the result will be like this for a calculation of both matrix from PR1 times PR2. And then lastly, I would like to explain about the bottom orthographic projections. So assume that we have the same cube again, and then the viewer of this who wants this in the front, and how about the viewer who wants to see in the bottom side? So the bottom will be like here. So this is the front view, and the viewer who wants to see the bottom view. What we need to do is we only move the object. We don't need to move the viewer. So by that, we rotate this one, the bottom one, to the top. So the bottom one, it will be the front here. So if we draw the axis, it will be x, y, and z. And then if we already move, the projection is most likely like this. So if we rotate this to the top, so the bottom view into the front view. So the z1 is over here, will most likely move to the top, since that we rotate it to the top, right? And then the y1 is going to the front of the z minus z, and then x still remain the same, since it is we rotate in the in x-axis. So that's why x still remain the same. Y prime is equal minus z, and then z prime is equal y. And then after that, we already got these equations, x prime, y prime, and z prime. And then we also know that this matrix for the bottom orthographic projections. And then after that, after we know the matrix, then we calculate the viewing transformations that equal PR1 times PR2. And then we have this matrix, this one, it will be this one, and times the PR2. So the result is most like this: 1 0 0 0 0 0 0 0 0 0 0 0 0 0 1. So this is the result for the bottom orthographic projections. And then, so I guess that's all from my presentations. So yeah, thank you so much, sir. You can also access my presentations in this one, bit.ly/orthoprojections. So I guess that's all. Thank you so much, sir.